Hello everyone, this is part 3 video on past year NEET questions from the topic gravitation. We'll start with a question that has come in the year 2012. The height at which weight of a body becomes 1/16th its weight on the surface of earth. We have to tell the answer for the height in terms of a capital R, which is the radius of earth. So basically what we are essentially looking at here is, if you look at a point which is at a height h, then the acceleration due to gravity over there g dash will be different from the acceleration due to gravity on the surface of earth, and weight of any body will be mass times the acceleration due to gravity. So as we go up, the acceleration due to gravity value will be in fact decreasing. So we look at a situation where the acceleration due to gravity g dash value will become 1/16th of the value of g on the surface of earth, and we have the general formula for acceleration due to gravity at a height h. G dash will be equal to g divided by 1 plus h by r whole power 2. We in fact have one more formula, that is the simplified formula, which is g dash is equal to g into 1 minus 2 h by r. This we use only when the h value is very small in comparison to r. So here in this case the g will not change significantly when h is very small in comparison to r, but over here the g is having a considerable change. So we have to use the general formula for g dash. So g dash will be equal to g by 1 plus h by r whole square. Now if you multiply both sides by mass, what we essentially get is on the LHS we have m into g dash, RHS we have m into g divided by 1 plus h by r whole square, and m into g dash is the weight at the height h, and m into g is the weight on the surface of earth. What is given is we are looking at the condition where the weight becomes 1/16th of its value on the surface of earth. Means w dash, we are looking at the value to be equal to 1/16th of w. So that means the w dash by w value will be 1/16. So 1/16 will be equal to 1 by 1 plus h by r whole square, and that will imply on cross multiplication 1 plus h by r whole square will be equal to 16. Now when we take a square root on both sides, we will get 1 plus h by r will be equal to 4, and if you bring the 1 onto the RHS, plus 1 becomes minus 1. So what we have is h by r will be equal to 3. In other words, h will be equal to 3r. So if we go to a height which is equal to 3 times the radius of earth, then the weight becomes 1/16th of its value on the surface of earth. So the correct answer is option C, which is the height value will be equal to 3 times the radius of earth. Moving on to the question that has come in again 2012. A spherical planet has mass mp and diameter dp. A particle of mass small m falling freely near the surface of this planet will experience an acceleration due to gravity equal to. So the acceleration due to gravity on the surface of the planet will be equal to g into mass of the planet divided by radius of the planet square, and g into mass of the planet. Since they didn't give the radius, they have given the diameter. So what we have is the diameter of the planet divided by 2 square. So acceleration due to gravity will be equal to g into mass of the planet by 2 square will be 4. So 4 will go to the numerator. 4 into g into mass of the planet by square of the diameter of planet. So the option A is the correct answer, and we know that acceleration due to gravity doesn't depend upon the particle mass. Next, another question that has come in 2012. A geostationary satellite is orbiting Earth at a height 5r above the surface, where r is the radius of the earth. The time period of another satellite, we have to find the value in hours, at a height 2r from the surface of earth. So we have one geostationary satellite whose time period will be 24 hours, which is orbiting at a height 5r above the surface of earth. And we need to find time period of another satellite which is orbiting at a height 2r from the surface of earth. So here we have the time period of the revolution relation to the radius of the orbit. As per the Kepler's law of periods, we have t square proportional to r cube, or t proportional to r power 3 by 2. That means if we take the ratio of the time periods t2 by t1, it will be equal to r2 by r1 whole power 3 by 2. And we'll assume that the t1 basically is 24 hours. This is for the geostationary satellite, and t2 is what we are looking to find. So the corresponding value of r1 is the geostationary satellite is at a height 5r above the surface. So if it is at a height 5r, the total orbit radius will be 5r plus r. And for the second satellite, which is at a height 2r, the orbit radius will be 2r plus r. So on substituting the values, the r2 value is 2r plus r, which is going to be 3r, and r1 value is r plus 5r, 6r. So 3r by 6r, it will be 1 by 2. So what we have is t2 by t1 will be equal to 1 by 2 power 3 by 2. And since t1 is the time period of the geostationary satellite, it is 24 hours. So it will give us the t2 by 24 is equal to 1 by 2 power 3 by 2. And 2 power 3 by 2 is basically 2 power 3 is 8. So root of 8, or 8 power half, root of 8 will be 2 root 2. So what we have is t2 will be equal to 24 by 2 power 3 by 2. And 2 power 3 by 2 will be nothing but 2 root 2. So 2 ones are 2 12s, and we can see 12 by root 2. When we multiply both numerator and denominator by root 2, what we have is numerator will be 12 root 2, denominator will be root 2 into root 2, it will become 2. So 2 ones are 2 6. So the final answer will be 6 root 2 hours. Option C is the right answer. Next question that has come in the mains paper 2012. If VE is the escape velocity and VO is the orbital velocity of a satellite for the orbit close to the Earth's surface, then the relation between the two. So if you look at the escape velocity from the surface of a planet, it will be root 2g into mass of the planet by the radius of the planet. And in general, the orbital velocity will be root gm by r, where r is the orbital radius. If we have a satellite orbit which is close to the surface of Earth, then the orbital radius value is nothing but the radius of the planet, because the orbital radius will be measured from the center of the planet basically. So wherever the satellite is there, we will measure the distance from the center of the planet. So if the satellite is close to the surface, then the orbital radius also will be equal to the radius of the planet. So that means we have the orbital velocity which is equal to root gm by again capital R. Now when we look at these two, the relation that we have is we can see that the root gm by r will be a common factor. So VE is in fact nothing but root 2 times of VO. So option D is the right answer. Next we have a theoretical question again that has come in 2012, the mains paper. Which one of the following plots represent the variation of gravitational field on a particle which is at a distance small r due to a thin spherical shell of radius r? So we have the shell theorem. This is a question straight based on the shell theorem. So we are looking at a shell of radius capital R, and the gravitational field that is developed because of the shell. So we are trying to plot the variation as a function of small r, where small r is measured as a distance from the center of the spherical shell. And we know, as per the shell theorem, the gravitational field, because of shell, inside the shell, at any point inside the shell, will be 0. So field inside will be 0, and on the surface the value of the field will be gm by capital R square, where the capital R is nothing but the radius of the shell. And if we look at points outside, the field value will be gm by small r square, where small r will be the distance measured from the center of the shell. And this, in fact, you can see is a function which is going to be a decaying function. As the value of small r keeps on increasing, the field value will be decreasing. So until r value is less than capital R, the value of field is actually 0. At exactly the smaller value equal to radius of the earth, it is becoming gm by capital R square, and after that it is going to be decreasing in exponential manner. So we see that option B here, until the radius is equal to capital R, or the distance from the center is equal to capital R, the field value is 0. There is no graph, as you can see here. It is on the x-axis, and suddenly it is becoming the highest value, gm by capital R square. This corresponds to, and then it is exponentially decreasing. So the correct graph that represents electric field variation is option B. Next, moving on to the question that has come in the year 2011. A planet moving along an elliptical orbit is closest to the sun at a distance r1 and farthest away at a distance r2. v1 and v2 are the linear velocities at these points. Then the ratio of v1 by v2 is. So we have to comment on what is the v1 by v2 ratio in terms of r1 and r2 relation. So if you look at a planet which is revolving around the sun in an elliptical orbit, so we'll have sun at one of the focal point. So we'll have two focal point for the ellipse, and the planet is basically revolving in the elliptical orbit. So at any location, if v is the velocity and r is the radius, then the angular momentum, so for the planet, the angular momentum value will be equal to m into v into r, and this is going to be remaining constant throughout the motion of the planet. That means since mass of the planet is going to be constant, if you look at two locations, one is the closest point and second is the farthest point, m into v1 r1 will be equal to m into v2 r2. So m is cancelled. So what we have is v1 by v2 is going to be equal to r2 by r1. So the correct answer is option B. So here we are using the concept of conservation of angular momentum. In fact, in Kepler's law, we study this as law of areas. So law of areas is nothing but implication of the conservation of angular momentum. Next, a question that has come in the year 2011 means a particle mass m is thrown upwards from the surface of the earth with a velocity u. The mass and radius of the earth are capital M and capital R. Capital G is the gravitational constant, small g is the acceleration due to gravity on the surface of earth. The minimum velocity or the minimum value of u, so that the particle does not return back to the earth is. So essentially what they are asking is the escape velocity. So the minimum velocity that is required so that the object or particle will not come back to the surface of earth is what we call as the escape velocity. Now we can quickly, we either use the straight away formula, or we can even derive this escape velocity over here. So if you look at the particle of mass small m on the surface of earth, then let us say we are giving it a velocity u. So initially the kinetic energy value will be half m u square, and potential energy value, since mass of the Earth is m and radius is r. The distance of the particle from the center of the Earth is capital R. So the potential energy will be minus gmm by r. So the total energy initially will be half mu square minus gmm by r, kinetic energy plus potential energy. Now as the particle goes away, if it goes to infinity, the potential energy value in the final stage will be 0. And if you are looking at the minimum velocity that is needed here so that the particle can go to the infinite location, we assume that the kinetic energy final also just becomes equal to 0. So under this condition we are looking to find what is the value of u. So that would mean that the entire RHS is 0. So half mu square will be equal to gmm by r, and u square will be equal to gm by u square by 2 is equal to gm by r. That means u square will be equal to 2 gm by r. U will be equal to root 2 gm by r. This is what we call as the escape velocity from the surface of a planet. So the correct answer is option B, and escape velocity does not depend upon the mass of the particle. Next, a question that is related to the gravitational potential. It has come in multiple years. Particle mass M is situated at the center of a spherical shell of mass same. So we have a spherical shell whose mass is also equal to M, and the particle is situated at the center of the spherical shell. The radius value of the shell is a. The magnitude of the gravitational potential at a point situated at a by 2 distance from the center. So we have to find what is the gravitational potential at a point which is situated at a by 2 distance from the center of the shell. And here when we observe the representation given here, so we have the shell where the mass will be only on the outer surface of the shell, and the mass of the shell is M. And we have a particle mass, again same M, which is at the center O, and we are marking the point P to be the location which is at a distance a by 2 from the center of the shell. Now at P we'll have two gravitational potentials, one because of the shell and other because of the particle which we are keeping at the center or which we are keeping at O. The overall gravitational potential will be the sum value or the addition, because gravitational potential is a scalar quantity. So when at a location multiple gravitational potentials are developed, we can just simply add them like scalars. So if we look at the gravitational potential at P due to the particle at O, so gravitational potential, so if you have a point mass of say m at a distance r from it, the gravitational potential value will be minus gm by r. So the distance from O to P is a by 2, so minus gm by a by 2. So that is the potential that is developed because of the particle m which we are keeping at the center of the shell. And one of the results of the shell theorem is that the gravitational potential at any point inside the shell will be always equal to the gravitational potential on the surface of the shell, and whose value will be equal to minus gm by a. So due to the shell, potential at any point inside the shell, irrespective of the location of the point, will be always equal to potential on the surface of the shell, whose value will be equal to minus gm by a. So this is the potential that is because of the spherical shell. So the overall potential is nothing but v1 plus v2. So minus gm by a by 2 plus minus gm by a. So that 2 will go to the numerator, minus 2 gm by a minus gm by a. So overall what we have is minus 3 gm by a, and as we know gravitational potential will be always negative. So if you just look at the value, the value is going to be 3 gm by a. Option C is the right answer. Moving on to the question that has come in the year 2010. The radii of circular orbits of two satellites A and B of Earth are 4r and r. So these are the radii values of the satellites of the Earth. if the speed of satellite A is 3v, then the speed of the satellite B will be how much? So here we are looking at a relation between the orbital velocity of the satellite and the radius. So we know that the orbital velocity will be root gm by r. So where capital M represents mass of the planet, capital G is the gravitational constant, and r is the orbit radius. So if you look at the relation, what we have is v is inversely proportional to root r. That means VA by VB is going to be equal to root of RB by RA. And here what is given to us is the speed of A is given as 3V, sorry. So 3V by VB will be equal to root of RB. Radius of the B is basically R, and radius of the A orbit is 4R. So what we have is 3V by VB is equal to root of 1 by 4, means it is 1 by 2. On cross multiplication, what we have is 6V is equal to VB. So the velocity of the satellite B is going to be 6V. Option B is the right answer. Next, a question that has come in the year 2010. A man of 50 kg mass is standing in a gravity-free space. Means there is no gravitational force acting on the man. At a height 10 meter above the floor, he throws a stone of mass 0.5 kgs downwards with a speed 2 meter per second. When the stone reaches the floor, the distance of the man above the floor will be how much? So when the stone is reaching the floor, we need to find what is the distance of the man above the floor. So we have a man who is initially at a height of 10 meters. So his mass is 50 kg. He is throwing a stone towards the floor, and the stone mass is 0.5 kgs. If the stone is reaching the floor, means stone is actually covering a distance of 10 meters. Now since we're talking about a gravity free zone, on the stone and mass as a combination or as a system, there is no external force acting on it, and that would mean that the center of mass acceleration will be 0, and since initially both are at rest, the velocity of center of mass, in other words the momentum of center of mass, which is the total mass into the center of mass velocity, must be conserved. So that would imply whatever the position of center of mass should not be changing with respect to time. So the product of mass of the stone into the distance the stone is covering, which is 0.5 kgs into the distance it is covering is 10 meters, will be equal to the product of mass of the man, which is 50 kg, into the distance the man will cover. So man will in fact cover the distance in the opposite direction. So we'll see that 0.5 kg into 10 meter divided by 50 kg will be equal to d value. So 0.5 ones, 0.5 hundreds, and d will be equal to 0.1 meter. So if the man is covering a distance of 0.1 meter in the other direction, the distance of the man above the floor at this instant is going to be, already previously it is 10 plus another 0.1, so it is going to be 10 plus 0.1, it will be 10.1 meters. This will be the distance of the man above the floor. Option B is the right answer.